Welcome back to the deep dive. Today we are jumping straight into the architecture that basically unlocked the modern LLM as we know it, flash attention.
Right. And our mission is really to get into the weeds on the algorithmic and, frankly, the engineering genius that finally broke that scaling wall for context windows.
And it all starts with what feels like a huge, a global misdiagnosis.
It really was. For years, everyone was laser focused on the computational cost of attention, the FLOPs.
The raw number crunching.
Exactly. But the breakthrough papers showed that the real problem, the actual barrier, was never the compute. It was the Dolen memory requirement.
Okay, hold on. If everyone knew attention was quadratic for years, why did it take so long to pinpoint that the bottleneck was just storing the intermediate matrices, not calculating them?
I think it's because we tend to focus on the most obvious metric, the FLOPs. But for a sequence of, say, 64,000 tokens, that attention matrix alone is over 16 gigabytes.
Which just completely crushes most GPUs.
It's a non-starter. And that brings us to Flash Attention V1 and its core idea, I/O awareness.
Right. The I/O part, the input-output, it's about data movement.
Precisely. On a GPU, you have this huge but kind of slow, high bandwidth memory, the HBM. Think of it as a giant warehouse.
Okay. Big but far away.
And then you have this tiny but incredibly fast on-chip SRAM. That's your desk drawer. Standard attention was constantly running back and forth to the warehouse. It was memory bound.
So the compute cores were just sitting there starved for data. So how did they fix it?
With kernel fusion, this is the key insight of V1. They took all the separate steps, the QKTA, the softmax, the multiplication with V, and fused them into one single GPU operation.
So all that intermediate work happens right on the desk in the fast SRAM.
Exactly. Those huge $1 times Noah matrices S&P are never even written out to the slow HBM warehouse. They live and die inside that one kernel.
That makes sense. But what about for the backward pass and training? You need those values, right?
And that is the other piece of brilliance. The recomputation trick. Instead of storing that massive probability matrix P, which would eat up all your memory,
I just recalculate it.
you just recalculate the block you need on the fly inside the fast RAM.
But wait, that sounds like you're doing more work, more computation.
You are. But you're trading a painfully slow trip to the memory warehouse for an incredibly fast on-chip calculation. And that trade-off is a massive win.
So you get one of memory and what? It was like a 7.6x speed up?
On the attention block alone, yes. It proved that being smart about memory I/O is way more important than just minimizing FLOPs.
Which then brings us to the evolution, to Flash Attention 2. Because they didn't stop there.
No, FA2 was all about engineering polish. They'd solved the external memory problem, now they looked inward. They used things like a split queue scheme to manage traffic on the chip's shared memory even better.
Pushing that MFU, the model FLOP's utilization, up to what, 72%?
On the A100, yeah. They were squeezing every last drop of performance out of the hardware.
And then with FA3, they went even further. It became a co-design project with the hardware itself.
Right, for the Hopper H100 architecture. This is where it gets really interesting. They started using specialized hardware blocks, like the Tensor Memory Accelerator, or TMA.
Which is basically a dedicated data-moving pipeline on the chip.
It's a superhighway for data, and it lets them completely overlap computation and I/O. You're crunching the numbers for one block while the TMA is already fetching the next one.
And that gets you to those insane numbers, like 1.2 petaflops per second.
With FP8 precision, yes. It's a perfect marriage of algorithm and hardware.
And the best part for you, the developer listening, is that a lot of this just happens. You get it for free.
Mostly, yeah.
Good.
PyTorch 2.0 has this scale.product attention dispatcher, SDPA. If you're using the right data types, like FP16, it just automatically routes your code through Flash Attention under the hood.
So let's tie it all together. By breaking that quadratic memory wall, Flash Attention is the direct enabler for the long context models we have today. The 8K, the 32K, all of it.
It's not an exaggeration to say the current generation of LLMs wouldn't exist without it.
So the big takeaway here is that the algorithm and the hardware are just inseparable now. The biggest gains aren't just from a smarter algorithm, but from an algorithm that deeply understands the physical layout of the silicon it's running on.
Totally. It's this philosophy of fusion, tiling, recomputation. It's all about being I/O aware.
Which really makes you wonder, if this worked so well for attention, what other parts of the transformer are just sitting there wasting cycles, waiting for a trip to the memory warehouse? The next frontier isn't just better models, it's finding all those other hidden bottlenecks.